Hey, D. Dykstra here again on graphing polynomials. Another great video here. So let's check this out, graphing polynomials. Polynomials is greater than x squared, which is a quadratic function. So we're talking about cubics, we're talking about functions to the fourth power, to the fifth power, and so on. And so we want to get some basic idea and some strategies down on how to graph these polynomials and what are some things to help us take a look and understand some of the basics as we go about this. So I've written up some strategies here, and if we look at these strategies, we notice that number one is know the basic function, right? What kind of function is it? We understand that if it's an x squared and it's positive, it's going to be a parabolic in shape and it'll point up, so look like a parabola. If it's negative x squared, then that means the a value here is negative, and so both arrows are pointing down. From there, we go to the cubic function. If it's a positive cubic, we know we're going to fall to the left side and rise to the right as the end behavior of that function. If it's a negative x cubed, then that means it's going to rise to the left and fall to the right. And then from there, everything else falls into place. In terms of if they're even or odd exponents, what will their end behavior like? So if it's x to the fourth, we know if it's positive, they're both going to be going up. If negative, they're both going to be going down. If it's an x to the third or fifth or seventh, then either positive or negative, right? We do the little disco move to help us remember that. They'll be going in opposite directions depending on the a value out in front, that leading coefficient. Everything is, again, determined by the leading term of the function. Remember that n minus 1 is the number of turns. So in this case, it's squared, so we have one turn. There's only one place for our turns. In x cubed, there are two turns, so we should expect that there's one turn and there's two turns, right? Same thing here. Then, we need to factor to find the zeros. We want those x-intercepts, so maybe we have to factor by grouping, maybe factor out a greatest common factor, maybe there's an x involved, something like that. We want to locate those zeros. Then, we have to recognize the multiplicities. Now, multiplicities are when you have zeros that are either one multiplicity or two or even or odd. So we recognize that odd multiplicities are ones that go through the x-axis, and evens tend to bounce. And then once we know the general shape, we can start to get an idea of what that graph will look like. Then we can find a midway value between the zeros. We want to use those to approximate the max and min. Again, this is just a sketch. We are not trying to be super calculating here with our ideas. All we want to do is just get a general idea. We might be off a little bit on where that max or min is, but right now that's basically what we're trying to do, is just get an idea of what the general look is like for these polynomials. Then find the y-intercept, and that always helps as well. So, all right, let's take a look at an example. We are given f of x equals 2x cubed minus 3x squared. So the first thing we do is we diagnose, right? Just like any doctor would do if they're looking at the patient. We go, okay, well, what's the deal here? Look at our leading term. Our leading term is positive, right? And it's a cubic. So it's a cubic function. It's positive, so I know in general it should look fairly close to this when I'm done. We notice that there's two turns, right? It's the n value is 3, so we know there will be two turns involved. So I factor this. Step 2 was to factor out. So what I did was I noticed that each piece in common, each term has an x squared in common. So I factored out an x squared, and I get 2x minus 3. Then, of course, with factors, we set them equal to 0, and we figure out what the 0 is. So x squared, set that to equal 0. X will equal 0. If I set 2x minus 3 equal to 0, then we get x is equal to 3 halves, right? We add 3 to both sides, and then we divide by 2. We get a positive 3 halves. Now, this x squared is a square, right? This is an even multiplicity, so we know that this one will bounce. Yes, will bounce. So it's a bouncer, right? We know it's going to skip off that x-axis there. Whereas 3/2, that has a multiplicity of 1, and so we know that at 3/2 this will go through. So x squared, again, has a 2 multiplicity, so it bounces at x equals 0. Then, we just find a couple other points. I know that if my x is at 3/2, then I know that around 1 there's going to be maybe a max or min, because at 0 it's going to bounce and then go through at 3/2. So I want to evaluate some values, some other x's to help me draw. So I'm going to go to the left, right? Because at 0 it's going to bounce, but it's this general shape. So what's happening at x equal -1? Well, if I plug -1 into the function, we get 2 times -1 cubed minus 3 times -1 squared. -2 minus -3 is -5. So I know that's another point I can use on my graph. If I look at f of 1, then I get 2 times 1 cubed minus 3 times 1 squared. We get 2 minus 3, or -1. So let's look and see what this graph does. Here we have it. I know that at -1 it goes to -5. I know it bounces at 0. Right? Got a big 0 there, but it's a bouncer. So I know that keeping in that general shape, I'm going to go up through -5, bounce at -1. Now I already calculated where about +1 would be, so I know that that ends up at -1. So there again is another point. I bounce there, I go through, and here's 3/2, right in between 1 and 2. So I know that goes through, and then my function will go off into infinity in the positive direction. So that's generally what our function looks like here. All right, let's take a look at another example. This time we have f of x equals x to the 4th plus x cubed minus 4x squared minus 4x. So, again, we go through what is the general shape. We look at this leading term. It's positive. It's x to the 4th. So we know in general it's going to have this W-type shape with 3 turns. 1, 2, 3 turns. So it should look about like this when we're done. Now, we can factor this. Now, I chose to do a factor by grouping just because I know that many of us aren't used to grouping, but this is the methodology behind grouping. Of course, there is a general x in each one of those. If I factored out an x, then I would get down to a cubic, and then I could factor it from there. But I recognize right away that this could fall into the grouping method, and so I wanted to go through that on this video with you. In grouping, what we do is we identify the first 2 terms and the last 2 terms. And the idea is that when we're done factoring out, we need to build the same piece here, right? The same factor. And then we can factor that out. So what I did was I recognized, oh, well, in this group here, an x cubed can be factored out. So there's my x cubed. In this group, I can factor out a -4x. And when I do that, each group will be left with an x plus 1, which is exactly what I want. If you get x plus 2 over here, grouping won't work. It have to be the same factor as these two are right here. So then, I bring my x plus 1 down, and I connect these 2 terms, x cubed and $-4x. That goes here. Now this is done. I can't factor this any further. But I look to this factor, and I say, oh, well, wow, there is something else involved there. So what can I bring out? An x. So I factor out an x, which leaves me x squared minus 4 times x plus 1. Am I done? No, I'm not. We recognize, look, something that is a perfect square minus something else that's a perfect square. What do we call that? A difference of 2 squares. Absolutely. So here's our final factors. X times x plus 2 and x minus 2. Those two come from here. right? And x plus 1. So my zeros of the function are x equals 0, x equal negative 2, x equal positive 2, and x equal negative 1. So, if I'm moving over here, I'll show you this graph. Come on over. Now we see that on our graph, I've got negative 2 as a 0, negative 1 as a 0. It goes through the x-axis at 0, as well as it comes back around through at positive 2. So in general, I know that my function will start off here. It's going to go through the x-axis at 2, right? And keeping in general with that same shape, I wanted to know what's happening between negative 2 and negative 1. Well, here I plugged in negative 3/2, which is negative 1.5, and I get about negative 1.3. So just a little over. So that gives me this nice curve here, and I go back up through negative 1. Well, what's happening at negative 1/2? Well, at negative 1/2, it's 0.9375, and I know I'm using a calculator here, but that's okay. We might have to do that sometimes. I could plug in 1/2 and do all that, but not enough time in this video to show you all that, so I just got some figures for us. Comes around here, and then I know it goes back through 0. And all of these go through because you notice that their multiplicity is all 1. There's no bouncers in this function. And then at positive 1, I found out that it goes through negative 6. So my function will go down here, and right at negative 6, or 1 and negative 6, it'll turn back around and go back up through to positive infinity. And if you notice, we end up with the same shape as what we thought, some kind of W-looking shape. All right? Well, hey, I hope that helped. This has been Graphing Polynomials, D Dijkstra. Hope you enjoyed that. Thanks again. And if you need to pause, rewind, go through it. Talk to you soon. See ya. Peace.